Hello, my name is Robert Smith, and I'm with New River Community College. And today we're looking at a titration between a strong acid and a weak base. This is very similar to the previous video of a weak acid and a strong base. So we're just going to do 1 point, and that'll be the equivalence point. So we're asked to calculate the pH at the equivalence point when 50 milliliters of 0.2 molar ammonia is titrated by 0.2 molar of hydrobromic acid. So the reaction that we're interested in is ammonia plus hydrobromic acid will give us NH4Br, which NH4Br is going to dissociate into NH4 plus Br minus. Okay, so first we want to calculate the number of moles that are involved. So that's going to be the number of moles of ammonia. So we're going to say N sub B, and that's going to be 0.0500 liters times 0.200 molar. That's volume times concentration in molarity. Just make sure that your volume is in liters when you do this calculation. And that gives us 1 times 10 to the minus 2 moles. Okay, so now we can use that information to do an ice problem. So we can do NH3 plus HBr is going to give us NH4 plus Br minus. So this is a neutralization reaction, so it's a one-way reaction. And basically it's going to be whatever has, because it's at the equivalence point, we already know that these are going to be zeros. So the moles of our ammonia are going to equal the moles of the HBr. So let's just put arrows. So then this one, we're starting off with 0 ammonia. We're not going to worry about bromide ions because they're spectator ions. So let's just focus on ammonium. And it starts off as 0, and we're going to add 1.00 times 10 to the minus 2. So the total is 1.00 times 10 to the minus 2. Okay. And so now we want to calculate the concentration. And in order to do that, we have to, concentration of ammonium. In order to do that, we take the number of moles times 10 to the minus 2, and we divide it by the total volume. And the total volume, because this is a monoprotic reaction, the volumes between the two, the acid and the base, are going to be the same at the equivalence point. So in this case, it's instead of being 0.05 liters, it's 0.10 liters. So once we do that calculation out, we find that our molarity is 0.100 molar of ammonium, which is half of what the molarity was for either the HBr or the ammonia rather, and that's what you would expect under these conditions. So now we can go to the next stage, next ice table, where we have NH4 plus, and we think about what that's doing in water. Well, that's going to give us back NH3, and a proton. And we're going to do an ice table. And we start off with 0.100 molar. We're working in molar here. And no ammonia and 0 protons, free protons. And we're going to take out an X on one side and then add it to the other as the concentration changes. So and once we have that, we can use our Ka for our ammonium, which is 5.6 times 10 to the minus 10, and set it equal to the products over reactants, so x squared over 0.100 minus x, which we're going to say is approximately x squared over 0.100. When you solve for x, you're also solving for the concentration of protons from this term over here. And that ends up being 7.5 times 10 to the minus 6. And once you've solved for that value, you can take the pH, which is equal to the negative log of 7.5 times 10 to the minus 6. And that should be molar, which gives us a pH of 5.13. If you recall from the previous video, the pH at equivalence, because you were using a strong base, was higher than neutral. And here, because we're using a strong acid, the pH is lower than neutral. So that's another sanity check that you can use when you're dealing with these kinds of problems.